So we want to introduce a new concept, a new definition called the order of an element. So let's say you have a group G and an element A. We say that A has finite order provided A to the K equals E for some positive integer K. So if you're able to find some positive integer K and take A to the K and get back the identity element, then you have finite order. The order of A, and we denote the order of A with the absolute value symbol around A, that's the smallest. It's the smallest positive integer, n, such that A to the n equals E. So the order of A is the smallest positive integer such that A to the n gives you back the identity. And if there is no positive integer K at all, where A to the K equals the identity, then A is said to have infinite order. Okay, so let's try to wrap our heads around this. Do some examples just for fun first. Examples. Determine the order of the element in the group. Okay, so number one, I want to look at 1 bar in the group C4. One bar in the group Z4. So what we want to do, we want to find the order of 1 bar. So we're going to write this absolute value symbol here around 1 bar. And we're going to figure out what do you have to, how many copies of 1 bar do you need to get back to the identity in Z4? So think about Z4. So Z4 is an additive group, right? Z4 under addition forms a group. It doesn't form a group under multiplication, right? Z4 has a 0 element. 0 element has no multiplicative inverse. So Z4 has to be an additive group, can't be a multiplicative group. So we have to figure out how many copies of 1 bar are we going to take. So I take 1 bar. 1 copy would just be 1 bar. That doesn't get you to the identity. The identity element is the 0 element when you're talking about Z4. Z4 under addition. 1 bar, 2 copies, that would be what? Actually 1 bar plus 1 bar, which is 2 bar. That doesn't get you back to the identity element, the 0 element. So you could take 1 bar, take 3 copies of it. That would be what? 1 bar plus 1 bar plus 1 bar. That would be 3 bar. That doesn't get you back to the identity element. So let's take 4 copies of 1 bar. 1 bar, I'm going to say the 4th power. I'm just going to say 4 copies of 1 bar. So that's 1 bar plus 1 bar plus 1 bar plus 1 bar, which is 4 bar, but we know 4 bar is 0 bar in Z4. So we definitely have finite order because we were able to get back to the identity element. And the order is 4. Right? 4 is the smallest number of copies of 1 bar you could take to get back to 0 bar. Now, most of the time we don't use the exponent notation. We're talking about additive groups, so we could have actually written this as 1 in front of 1 bar, right? Rather than having a 1 up there. And this one, the second one, rather than putting a 2 out front, a 2 up top there, you could have had 2 1 bars. 2 copies of 1 bar in this one. Rather than using the exponent notation, you could have used the additive type notation where it looks like multiplication 3 of 1 bar. And this last one, you could have used 4 copies of 1 bar. This is another way to write it. This is the typical additive notation you would use rather than the exponent notation. But it means the same thing in the context. Because you only have one operation, right? You don't have the multiplication here in this group. You only have addition. You could write it either way. Okay, so the order is 4. The order of 1 is 4. You had to get 4 copies of 1 bar to get back to the additive identity 0 bar. Okay, let's do number 2. Let's talk about 3 bar in the group U8. Now let's think about what U8 is. U8 is a multiplicative group, right? It's the units of Z8. So we're in Z8, we're in the integers modulo 8, but we're only looking at units. So those things that are relatively prime to 8. So 1 bar, not 2 bar, 3 bar, not 4 bar, 5 bar, not 6 bar, 7 bar. That's it. So it has 1, 2, 3, 4 elements. And we're modulo 8. So if I wanted to look at 3 bar, and remember that, so this is what, U8 under multiplication. So we'll stick with definitely just the exponential notation. We'll start 3 bar to the 1 power. That gives you 3 bar. That doesn't get you back to the identity. So here the identity element is 1 bar, right? 1 bar, this is the identity element right here. Under Z4, let me go right down here for Z4. Z4 was just what? 0 bar, 1 bar, 2 bar, 3 bar, that was Z4. And this was the identity right here, 0 bar. Well, underline that. Okay, so I did 3, so going back to U8 now. Look, trying to find the order of 3 bar. 3 to the 1 gives you 3. That doesn't get you back to 1. What if I do 3 bar to the 2 power? That's going to mean 9 bar, right? But 9 bar is the same as 1 bar in Z8. So that means we have, this element has finite order, and it's order 2, right? We only needed 2 copies of 3 bar to get back to the identity. Okay, so I forgot to put a 1 bar here. And problem 1. Okay, now problem 2. So we're going to take the order of 3 bar. The order of 3 bar is 2, right? We're going to take 2 copies of 3 bar to get back to the identity. Okay, let's do a number 3. Number 3. Let's say we're talking about the matrix I don't know. Stomach growling. Matrices? No, let's do permutations. Let's talk about this permutation. 1, 2, 3, 4. Those are our inputs, and our outputs are going to be 3, 4, 1, 2. And we want to look at this in S4. S4, so all the permutations of 4 objects. So S4 is under functional composition. That's our group. S4, comma, functional composition. So we want to find the order of this. 1, 3, 2, 4, 3, 1, 4, 2. Find the order of them. So we're going to compose it with itself a bunch of times. So if I write 1, 2, 3, 4, 3, 4, 1, 2, to the 1 power, that means I just have it 1 time. Okay, if I do this to the 2nd power now, that means I'm going to compose it with itself. I'm going to have 2 copies of it. I'm going to have 1, 2, 3, 4, 3, 4, 1, 2, 1, 2, 3, 4, 4, 3, 4, 1, 2. So how do you compose? You start off with these, 1, 2, 3, 4. You're going to write those over the top. So 1 goes to 3. And, hold up. And 3, shoot. and 3 goes to 1. So I'm going to put a 1 here. Let's see. 2 goes to 4, and 4 goes to 2. So I'm going to put a 2 here. 3 goes to 1, 1 goes to 3. 4 goes to 2, and 2 goes to 4. So I'm going to put a 4. Hey, look at that. I got back to the identity. This is the identity permutation. 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. So it only took 2 copies to get me there, right? 2 copies. So my order here is going to be 2. I got any matrix examples? I thought I had a matrix example. Yeah, I got a matrix example. Let's do a matrix example. This is going to be number 4. So here I have the element 1, 0, 1, 1 in the 2 by 2 matrices. So my group is going to be the 2 by 2 matrices. Oh, so sorry, the general linear group, the invertible matrices. G, L, 2 of R. Remember what this is. This is the set. This is the set of all matrices of the form A, B, C, D. So 2 by 2 matrices, such that AD minus BC is not 0. So the determinant's not 0. A, B, C, and D are real numbers. So all the invertible matrices that are 2 by 2. So this is definitely invertible, this matrix, right? 1, 0, 1, 1. 1, 0 in the first column, 1, 1 in the second column. It's definitely invertible because it has a determinant of not 0, right? Determinant of 1. So we want to find the order of this. So don't think of this as a permutation, just think of this as a matrix. Remember, the operation is matrix multiplication. So here I'm looking at GL2 of R, and I'll just put a little dot. That means matrix multiplication. So what are we going to do? We're going to start off with 1 copy. 1, 0, 1, 1. So raise it to the 1 power. You get 1 copy. Okay. What is the identity? The identity is the identity matrix. 1, 0 in the first column, and then 0, 1 in the second column. Let's see if we can get to the identity matrix. So I'm going to do it to the second power. 1, 0, 1, 1 to the second power. So I'm going to have 2 copies of that 1, 0, 1, 1. 1, 0, 1, 1. So how do you multiply matrices? First row, first column is going to be 1 times 1 is 1 plus 1 times 0 is 0. I'm going to do the first row, the second column. 1 times 1 is 1 plus 1 times 1 is 1. Okay, I'm going to do the second row, first column. I'm going to do 0 times 1 is 0 plus 1 times 0 is 0. And then I'm going to do the second row, second column. I'm going to do 0 times 1 is 0 plus 1 times 1 is 1. And I'm going to add that up. I'm going to get 1, 0 in the first column, 2, 1 in the second column. Okay, let's see what happens. We take the 3 copies of this, 1, 0, 1, 1, to the third power. Well, think about what that would be. That would be 2 copies, right? 1, 0, 1, 1, times an additional copy, 1, 0, 1, 1. Now, do we already know what the square of 1, 0, 1, 1 is? Yeah, we know it from the previous step, right? It's 1, 0, 2, 1. We're going to multiply that by 1, 0, 1, 1. So let's multiply. Okay, let's do the first row, first column. You're going to get 1 plus 0. Let's do the first row, second column. You're going to get 1 plus 2. Let's do the second row, first column, you're going to get 0 plus 0. And let's do the second row, second column, you're going to get 0 plus 1. This all turns out to be 1, 0 in the first column, 3, 1 in the second column. So you're probably starting to catch a pattern. I don't know if you can see the pattern. We'll do one more. 1, 0, 1, 1 to the fourth power. So that means I'm going to have, what, 1, 0, 1, 1 to the third power times 1, 0, 1, 1. Now we know that 1, 0, 1, 1 to the third power here. We did that in the last step. It's 1, 0, 3, 1 multiplied by 1, 0, 1, 1. So let's multiply these together. First row, first column multiplication, 1 plus 0. Okay, let's do the first column, first row, second column multiplication. It's going to be 1 plus 3. Let's do the second row. Come on, second row, there we go. First column multiplication is going to be 0 plus 0. And let's do finally the second row, second column multiplication is going to be 0 plus 1. So it'll be 1, 0, the first column, 4, 1, the second column. So you should see a pattern. I don't know, can you see that pattern? Notice here you have a 1, here you have a 2, here you have a 3, here you have a 4. So if you continue this, I mean, you can prove this by induction. I'm not going to prove it by induction, but if you want to, you can. You get 1, 0, 1, 1 to the kth power equals 1, 0, k, 1. This is for k greater than or equal to 1. K greater than or equal to 1. Yeah. I should specify that here. This is 4. K greater than or equal to 1. Right, we're not talking about 0 powers, just talking about. So anytime you're looking at order, you always have to have a positive exponent, never 0. Okay, so my question is it possible to ever get the identity matrix when you have positive k's? No, right? Because k is going to start at 1 and go up 2, 3. So it's never possible to get a k in an upper right-hand corner there. So what does that mean? If you never can find a positive integer to raise your matrix to as an exponent to get the identity matrix, so that means it has infinite order. That means this has, so we write this is equal to infinity. The order of that element is infinity because you can never raise it to a positive exponent to get the identity matrix. Okay. So just a little quick theorem we want to prove here. This is theorem 7.8. This is about distinctness of elements or non-distinctness of elements and how it applies to having finite order or infinite order. So let G be a group with A an element of G. Number one, if A has infinite order, that means there's not a positive integer k that you can raise A to get the identity, then the elements of the form A to the k are all distinct. A to the k, let me write it. A to the k are distinct. So a to the 1 is going to be different from a to the 2, which is going to be different from a to the 3. It's going to be different from a to the 4, which is going to be different from a to the 5. So if you have an element of infinite order, all of those elements will be distinct. So no two elements will be, like if I have a squared, there's nothing like a to the 299 it could ever be equal to. Number 2, if you ever end up with a to the I equal to a to the j, and the I and the j are different, let's pretend the I and the j, I get to say a squared equals a to the 99th or something. A squared equals a to the 99th. So I is not equal to j here. Yeah, so let's just pretend I had a squared equals a to the 99th, and that would mean that the element would have finite order. Then a has finite order. Okay, I'm actually going to prove 2 first, and then we'll prove 1 proof. Suppose G is a group with A and G. Let me say let G be a group. That's a better way to say it. Let G be a group. So we want to prove 2. So to prove 2, we're going to suppose that A to some power I equals A to some power j with, so these are positive integers. I is not equal to j. So without loss of generality, let's just pretend that I is bigger than j, okay? Without loss of generality. We could say j is bigger than I, but we're going to pretend. Let's just assume that I is bigger than j. So if that's the case, that means that I minus j, right, if you subtract j from I, you're going to get a positive number, right? So I minus j is going to be positive. Okay, so what we want to look at, what is a I minus j? A I minus j. Well, using your properties of exponents for elements of a group from earlier, we have a to the I starred a to the minus j. Now what does that mean? Well, remember that a to the I, another name for a to the I, right? We assumed that a to the I was the same as a to the j, so we're going to replace a to the I with a to the j. And that's times a to the minus j. Now, what is this exactly? A to the j is the same thing as just a to the j. And a to the minus j, one way you can write this is a to the j's inverse. This is the inverse of a to the j. So what happens when you take a to the j starred with a to the j's inverse? Well, you get the identity. So, what does that mean? Notice this I minus j right here. This yellow exponent is positive, right? I minus j back here. It's a positive integer. So since I minus j is a positive integer, so what do we have? We have a to a positive integer gives us the identity. That means a has finite order. Then a has finite order. That's the definition of having finite order. Okay, we've proven 2. 2 has been proven. Now, what happens when you take the contrapositive of 2? If you were to restate the contrapositive of 2, let's write that. This is how we're going to get 1. By contraposition of 2, So what would you do? You would say if the negation of that, if A has infinite order, then A to the I is never equal to A to the J. For I not J. So if A to the I is never equal to A to the J for all I's not J's, then that means that the A to the K's powers are all distinct. No two are ever the same. So therefore, thus, A to the K is distinct for each K. You can do that any integer, actually. End of proof.